Duality, inverse causality, and organism. Duality. Duality is a tool for understanding particle which is very organic. If the particle is organic enough, so the network happens among entire body of particle, then the particle has duality, which means two contrary properties are true in one system. Entanglement entropy. Entanglement entropy is a good tool to measure how much two regions are entangled. And the maximum entropy is limited, which is the value for duality to exist. And I'll show what is entanglement entropy. Consider a quantum system that is divided into A and B, two parts such that the four Hilbert space can be represented as the tensor product of the Hilbert spaces of A and B. Like this. A typical wave function of this system is psi is like this, in which A and B in the state psi are entangled, since psi cannot be written as a simple product of those of A and B. Entanglement entropy is a measure to quantify how much A and B are entangled. Define a reduced density matrix of A by tracing over a B state in psi. Then entanglement entropy is defined as this. From the definition, an obvious corollary is SA is 0, low denotes a pure state. Psi can be written as a simple product, and this for any pure state we can always write it as psi is like this. By Schmidt's decomposition of psi into some complete set of A and B, it follows that SA is SB. For AB composite system in a mixed state, in general we have SA is not SB. In such a case, entanglement entropy typically contains classical statistical correlation of the mixed state in addition to quantum correlations. Here are some examples. A two-spin system, we can have a state like this that is not entangled. However, the state psi is cosine theta down spin upspin plus sine theta upspin downspin is entangled. For this state, the reduced density matrix for A is like this. Shows entanglement entropy is SA is my cosine square theta log cosine square theta minus sine square theta multiplied by log sine square theta. We see SA has period of pi over 2. Theta and minima are SA is 0, which theta is n pi over 2, and maxima are SA is log 2 when theta is like this, where n is integral, and maxima the state psi is 1 per root 2. Downspin upspin plus upspin downspin is most entangled. We list some important properties of entanglement entropy as follows. Suppose ABC are three parts of the system without any interaction between any two of them. We have subadditivity and strong subadditivity. Entanglement entropy plays an important role in quantum information and quantum computation, as it provides quantitative measure of quantum correlations that are not present classically. Consider system AB. If Hamiltonian is HA plus HB, then the ground state is unentangled. Moreover, starting with a generous unentangled state, this system will remain unentangled. If we add coupling between A and B, H is HA plus HB plus HAB, then the ground state is generally unentangled. Suddenly, starting with initial unentangled state, entanglement will be generated during time evolution. In all realistic condensed matter systems and quantum field theories, HAB is a local Heisenberg model. And pi over 4 quantum field theory, Lagrangian is like this. Locality implies, as shown in the picture below, that the interaction only happens near the interface of A and B. So HAB only involves degrees of freedom near the A and DB. This has important implications. This is the locality of interaction. One finds in general in the ground state for a local Hamiltonian entanglement entropy given by given by like this, where epsilon is the lattice spacing for CM system or short distance cutoff for quantum field theories, which characterize the geometric width of interface. This formula shows that entanglement entropy between A and B is terminated by short-range entanglement near the A, where HAB is supported, while 16 appears to be universal. Number is not, depending on short-distance physics of large-range entanglement, and can provide important characterization of a system, characterized topological on the 2 plus 1 dimension. In typical gapped systems, ground state contains only short-range correlation. In topological order systems, ground state contains long-range correlation, now accessible via standard observables such as correlation functions of local operations. The entanglement entropy for such a system is like this, where gamma is not zero, is topological order, a constant independent of shape and size of A. Characterize the number of degree of freedom of a quantum field theory for a 1 plus 1 dimensional quantum CFT. There's no leading contribution, and one find like this essays like this, where C is central charge and L is the length of A. We know C contains the information of number of degree of freedom of a 2D CFT via Cardi formula for 2 plus 1 dimensional CFT. One finds like this, where gamma depending on the shape of A can be used to characterize the number of degree of freedom. Similar result can be found in other dimensions. Holographic entanglement entropy. Suppose we have a CFT with a gravity dual. How can you calculate entanglement entropy on gravity side? As shown in the picture below, we propose to find the minimal area surface gamma which extends into the bulk with the AS boundary, and entanglement entropy is given by like this. This formula was first guessed by SRT, who were motivated by black hole entropy. This is minimal area. There are some support for this formula. 1. Satisfy the strong subadditivity conditions. 2. Reproduce known results about entanglement entropy. 3. Give many new results that are sensible. While easy to define, entanglement entropy is very complicated to compute for a general many-body system. Even for free quantum field theory, the computation is highly non-trivial and often numerical calculations are needed. RT provides a very simple way to compute entanglement entropy in a class of strongly interacting quantum field theory. Here are proofs of strong subadditivity. In figure 3a, we can easily find this, and by definition of minimal surface, this, which implies this. In figure 3b, we also have this, and by definition minimal surface, which implies this. Now we can apply this formula to 1 plus 1 dimensional CFT whose duality 83, where the metric is this. We know each CFT is characterized by a central charge C, density of state is like this, and the trace normally gives this, where R is a Ricci scalar. For holographic CFT, the central charge is